Hello everyone, thanks for coming. Today we're going to do a review of our numerical analysis week 5 lectures. So in this week, we mainly talk about norms, inequalities, and fitting problems, as well as error analysis of numerically solving a matrix vector equation. So first, we reviewed vector norms defined in linear algebra. For a vector, the one norm is a summation of the absolute values of all entries of this vector. The two norm is taking the square root of the summation of the square of each entries of this vector. The inf norm is just the maximum of the absolute value of all entries. So we have several inequalities for vector norms. First, we have the Cauchy-Schwarz inequality that states the inner product of two vectors u and v is smaller than the 2 norm of u times the 2 norm of v. We have the Young's inequality, which states for two numbers we have a times b smaller or equal than a to the power p over p plus p to the power q over q, where p, q are positive and 1 over p plus 1 over q is 1. Based on the Young's inequality, we can derive the Holder's inequality, which states that the inner product of two vectors u and v is smaller or equal than the p norm of u divided by p plus the q norm of v divided by q, where p and q are positive real numbers and 1 over p plus 1 over q equals to 1. Finally, we have the Minkowski's inequality, which is also the triangle inequality for the norms of vectors. The p norm of a and a plus b is smaller than the p norm of a plus p norm of b. Based on the vector norms, we can define subordinate matrix norms. So the subordinate matrix norms of A, which is also called the vector-induced norm, is defined as the supremum for over all non-zero vectors V, such that AV, the norm of AV over V, is taken. The supremum over AV, the norm of AV divided by the norm of V is taken. So we have the subordinate matrix 1 norm, which is the largest column 1 norm. The subordinate matrix inf norm is the largest row 1 norm of the matrix. Finally, we have the subordinate matrix 2 norm. So it is defined as the square root of the spectrum of the matrix A transpose times A, which is the largest absolute value of all eigenvalues of the matrix A transpose A. So the matrix and vector norms are useful for analyzing the errors when solving a linear system. We also define the condition number. First, we have the absolute condition number. The local absolute condition number at x for function f is defined as the norm of f of x plus delta x minus f of x divided by the norm of delta x, taking the supremum of this quantity. For the condition number of a matrix, we define it as a kappa A, which is the norm, the subordinate matrix norm of A times the subordinate matrix norm of A inverse for some compatible vector norms. We have this arrow bound result. The norm of delta x over the norm of x, which is a relative perturbation in the outcome for solving ax equals to b, is smaller or equal than kappa A times the norm of the perturbation in the right-hand side vector b over the norm of b. So the norm in the relative error in the result can be bounded by kappa A times the relative error in the perturbation on the right-hand side vector b. So finally, we talked about the least square fitting. So when talking about least square fitting, A is not triangular square matrix. It is usually a triangular matrix, and usually the number of rows is larger than the number of columns, which means that we have more data points to fit than the number of variables. So we find x such that the 2 norm of ax minus b is minimized. To solve this problem, we are solving the normal equation, that is to find the solution x such that h transpose A times x equals to h transpose times B. Thanks for listening.